Okay, so hello everyone. My name is Patrycja Wegrzynowicz, and today I'm going to tell you about the security, or rather insecurity, of JSON Web Tokens. First, a short introduction. I've been doing professional software development for over 20 years. My interests focus on patterns and anti-patterns in software. I work on tools for automated detection and refactoring of software defects, such as, among others, security vulnerabilities. So basically, security is my daily job. What am I going to talk about today? First, a brief introduction to JSON Web Tokens, just for all of us to be on the same page. The key part of today's talk involves 4 demos that reveal some security problems with the spec, the implementation of token libraries, and some problems with our applications. There are a number of caveats which concern JSON Web Tokens, and we'll start with the first difficult thing, which is how do we actually pronounce it? And it turns out it's not a piece of cake. As a native Polish speaker, I pronounce it as JWT. In English, I usually hear the pronunciation as JWT, but the RFC suggests the same pronunciation as the English word JOT. By the way, JOT in English means a brief informal note, just as JSON Web Tokens are a short, less formal tokens. However, in today's talk, I will pronounce it as JWT. Why? Because I'm not sure whether I pronounce JOT clearly enough. Plus, from my experience, majority of developers are used to JWT pronunciation. So, JSON Web Token is a set of claims that encode users' identity and usually users' permissions. It also consists of a digital signature to protect its content against tampering. It's always handy to take a look at some sort of an example. Here we see that a JSON Web Token is a long string consisting mostly of letters and numbers. We can recognize 3 parts separated by dots. These 3 parts are a header and payload and a signature, all 3 base64 URL encoded. When we decode these 3 parts, we see that a header and the payload are just JSON strings. The header contains an algorithm used to generate a signature. In our example, it's HS256, HMAC with SHA256. The payload contains actual claims of a token. In our example, it contains 4 claims: subject, issued at, issuer, and expiration. And the signature is just binary content. Here, we also see the very first problem of JWT, the lack of confidentiality. The tokens are not encrypted. They are only encoded. So it's easy to decode them and see all data available in claims. Therefore, we should avoid enclosing any confidential information in claims. A JSON Web Token is generated on the server side, then it's stored on the client side, usually in the session storage. Then, with each subsequent HTTP request, the token is transmitted to the server, usually as part of the authorization header, as you can see on the screen. Then, on the server side, the token is verified, and in case of an incorrect token, the request is rejected. It sounds very simple. So now it's time for the reality check. Let's take a look at some security problems of JSON Web Tokens. So there are a number of caveats which concern JSON Web Tokens, And we'll start with the first difficult thing, which is how do we actually pronounce it? And it turns out it's not a piece of cake. As a native Polish speaker, I pronounce it as JWT. In English, I usually hear the pronunciation as JWT, but the RFC suggests the same pronunciation as the English word JWT. By the way, JWT in English means a brief informal note, just as JSON Web Tokens are a short, less formal tokens. However, in today's talk, I will pronounce it as JWT. Why? Because I'm not sure whether I pronounce JWT clearly enough. Plus, from my experience, majority of developers are used to JWT pronunciation. So JSON Web Token is a set of claims that encode users' identity and usually users' permissions. It also consists of a digital signature to protect its content against tampering. It's always handy to take a look at some sort of an example. We see that a JSON Web Token is a long string consisting mostly of letters and numbers. We can recognize three parts separated by dots. These three parts are a header, a payload, and a signature, all three base64 URL encoded. When we decode these three parts, we see that a header and a payload are just JSON strings. The header contains an algorithm used to generate a signature. In our example, it's HS256, HMAC with SHA256. The payload contains the actual claims of a token. In our example, it contains 4 claims: subject, issued at, issuer, and expiration. The signature is just a binary content. Here we also see the very first problem of JWT, the lack of confidentiality. The tokens are not encrypted, they are only encoded. So it's easy to decode them and see all data available in claims. Therefore, we should avoid enclosing any confidential information in claims. A JSON Web Token is generated on the server side, then it's stored on the client side, usually in the session storage. Then, with each subsequent HTTP request, the token is transmitted to the server, usually as part of the authorization header, as you can see on the example on the screen. Then, on the server side, the token is verified, and in case of an incorrect token, the request is rejected. It sounds very simple. So now it's time for the reality check. Let's take a look at some security problems of JSON Web Tokens. Before the first demo, some organizational information. I will need your cooperation during demos. I would like to show a live hijacking of your accounts. So my kind request to you, please go to the demo application, the link available at my Twitter account at Ion Labs, and also you can see on the screen. Please register your account and log in. So now it's time for the first demo. The first demo reveals a problem with the none algorithm. In JWT spec, there are only 2 mandatory algorithms to be supported by a library. The first one is HS256, and the second one is none. None basically means no algorithm, no signature. In my demo, I will show you how to use the none algorithm to bypass server verification. So now I'm switching to my browser. I will log in to the demo application. Please check out my Twitter. I've posted the link on my profile, Yon Labs. You can see the link here, demo.yonlabs.com. Now I'm switching to my demo application and logging in. Okay, so I see some user. Please log in. I will need a couple of more users to showcase live hijacking. Okay, perfect. As you can see, it's a simple application displaying a profile and the list of all users in the system. We have enough users to showcase a demo. When you take a look at the demo and your session storage, you see that there is a token. If we decode the token, we can see that the token uses HS256 algorithm plus a number of claims. Now, I will use this pre-prepared fake token, which uses non-algorithm, and the subject claim is set to number 3. The subject represents basically in my application the ID of a user. So now I'm copying the token and I will replace the token in my browser. Now refreshing the page and voila, damn it, congratulations, your account has been hijacked. So it was as simple as that. So the first question is, why was such a token accepted by the server? Because we have a vulnerability in our code. And unfortunately, it's a mistake one can make very, very easily. What's the mistake? At first sight, our verify method looks fine. However, it's not. We've used the parse method, which only decodes the token and does not verify signature. So instead of parse, we should use parse claims JWS. I must admit that the naming in this library is not very intuitive. And it's not the only library with the none problem. When we search the National Vulnerability Database, we can find many more issues related to JSON Web Tokens. One of those issues reveals the none problem in another library, Prime JWT. And check out the year of the entry. The issue was raised in 2018, so only 2 years ago. How many applications are not patched yet? Who knows? So basically, there are 3 main problems revealed by our first demo. The first problem is the presence of the none algorithm in the RFC. I guess that the intent was to use the none algorithm in some sort of a controlled environment, like internal network. However, even in such cases, it's not recommended from the cybersecurity point of view. The second problem is the misleading API in various JWT libraries. And the last but not least problem is with us, developers. We often don't read manuals, we use samples found in the internet, so such mistakes happen. To protect our code against such problems, we should understand the library we use. We should check out vulnerability databases. And in addition, in our code, we should also require a specific algorithm and a key during verification. Why should we require a specific algorithm and a key? Because otherwise we can end up with serious security vulnerabilities in our code, like this one, when a hacker can trick a vulnerable application to change the algorithm to HMAC SHA instead of RSA. Let's take a look at the attack scenario. For a regular user, the server generates a token signed with a server RSA private key, and the server verifies a sent token with a server RSA public key. For a hacker, the hacker generates a token signed with a server RSA public key used as an HMAC secret, and then the server verifies the token using the algorithm set by a hacker, and the server uses its public RSA key for verification. So that's it. A hacker can hijack any session. And here is another reason why to require a specific algorithm and a specific key. It's another vulnerability where a hacker can provide his own public key for the server to verify a token. Actually, the library followed the standard, and that was the root cause of the vulnerability. The standard specifies that a JSON web key representing a public key can be embedded within the header. And that's another problem with the standard. The main paradigm of cybersecurity is never trust a client. And here is a simple scenario how a hacker can provide a public key in the header. Here is something more optimistic. The library with a nice API design supporting security. Please note how strong typing and object-oriented programming help to achieve good security. So now it's time for the second demo. The second demo is the demonstration of a key cracking of HS256. HS256 stands for HMAC with SHA-256, hash-based message authentication with SHA. The algorithm requires a secret key. It's a symmetric algorithm, which means the same secret is used for generation and verification of a signature. As this is a symmetric algorithm, once you can get to know a secret key, you can generate your own tokens to be accepted by the server. So for password cracking, I will use Hashcat. Hashcat is a free and open source password cracker. Oops, sorry, it's not a password cracker. They call themselves a password recovery tool. So first, we need to grab a real token. So again, I will log in to my demo application. I will copy the token, and I have a simple script prepared just to pre-configure some configuration parameters for Hashcat. I will use this script to crack our secret based on our token. Hashcat is a very interesting tool because it performs brute force recovery very, very quickly. Why? Because it uses not only CPU, but also GPU for password cracking. So our password has been already cracked. It's Java. I've used very short password for the purpose of a demo. In your real world application, you should use strong passwords. So now, when we have the password, we can generate our own token. This time I will use the subject number 5. I will use the password Java, and we have a new token, which I will copy again to the session storage, and I will refresh the page. And now, instead of Patrycja, I'm logged in as Palo. So congratulations, Palo. You've been very helpful. The obvious problem revealed by our second demo is weakness of our secret key. Another problem is that for the key cracking, a hacker needs only one token, and all cracking is done offline, without any communication to the verification server. Therefore, there is no method to detect such brute force attack, and the victim and the server remains unaware of the attack. And once a hacker knows the secret, he can generate whatever token he desires, impersonating whatever user he desires. It turns out it's pretty complicated to adjust our keys and algorithms properly, as there are many algorithms and different kinds of key possibles. There are 4 main algorithmic families available. The first 2 are the most popular, HMAC with SHA and RSA with SHA. As it comes to HMAC with SHA, the recommended key length is as long as the length of the hash. So for HS256, at least 32 bytes. It's worthwhile noting that it's a symmetric algorithm, so the shared key is used for generation as well as for verification of the tokens. Therefore, the secret key must be present on each server. So when one server in our scalable infrastructure is compromised, the entire system is compromised, because once a hacker knows the secret, he can generate any token. In case of RSA with SHA, the recommended key length is 2K bits at minimum. And in case of RSA, it's an asymmetric algorithm. It uses separate public and private keys. Only authentication servers store the private key, and verification servers use only public key to verify tokens. Therefore, in case of a scalable infrastructure, the attack surface is decreased. So now it's time for our third demo. In third demo, I will steal one of your tokens by packet sniffing. I will log in to my server. The server is hosted on Oracle Cloud, and I will run TCP dump. I have again a short script prepared. Okay, so TCP dump is up and running, and now I will need your help. Please refresh your pages, and I will catch one of your tokens. And please be careful to use HTTP version, not HTTPS-based version of the application. So, oops. Can we have a short break? I will need to connect to the power source, and I will wait for your I will wait for you to refresh the pages. Oh, okay.
Yep, we're back. No problem. Can continue.
Oh, sorry for the problems. I'm back and I see a lot of tokens coming in. So thank you for your cooperation. So now for me, it's enough to copy one of the tokens. Oops, they are coming pretty fast. Okay, that's a token. Thank you. Now again, I'm switching to my demo and replacing the token. Refreshing the page, and now I'm banded. So you see that our theft was successful. So as you can see, the problem is that the stolen tokens can be used freely as long as they are valid. Another problem in our application was the lack of encryption. So instead of HTTP, we should use HTTPS. In case of HTTP, your tokens, your password are sent in plain text over the net. So any server which your packet passes during the transport is vulnerable to such packet sniffing. So in our previous demo, the problem was the lack of encryption. Now let's move to the encrypted communication channel. Let's use HTTPS, and still I'll be able to hijack your session. This time by exploiting an HTTPS vulnerability to steal one of your valid tokens. So I will post HTTPS link to my Twitter account. Please use this link to log in to the application, just to switch to secure channel. So in case of fourth demo, we'll use a stored XSS, which is present in our homepage field of the demo application. I have a simple JavaScript ready. It's this JavaScript. I will copy it, and I will update my profile with this malicious JavaScript. Now, my question and kind request to you, please refresh your applications and click my link, Patrycja account. In case of this malicious JavaScript, any user who clicks the links will trigger the JavaScript, and his or her token will be sent to the evil server. The only thing for a hacker now is to sit and observe upcoming tokens. I'm already logged in to my evil server, and I will observe logs. So please, now it's your turn to click Patrycja's link, refresh your pages, and click my link. Now I'm checking for any users to click. Now I will click myself. When I click, you see that the JavaScript is triggered, and besides of a token being sent to the evil server, the simple alert is displayed, which says that your JWT has been stolen. Okay. I see some tokens. Let's hope it's not mine. Possibly not, because I was not clicking at the moment. Okay. This one. Just to copy it. And again, replace the original token with the stolen one, refreshing the page. Oops, and now it's 000. Congratulations, your account has been hijacked. So here you can take a closer look at the malicious JavaScript. The only tricky part of this script is that we do not connect the evil server directly. We connect via loading the link as an image source. This way, we can bypass the same origin policy implemented by the browsers. Obviously, the problems with the fourth demo is that we have an XSS vulnerability in our application. So first, we should apply the best anti-access practices to avoid such vulnerabilities. And the other problem is that there is no other way to block access to a session storage for JavaScript. However, in case of hardened cookies, we can block such access. So it might be better to use hardened cookies as a storage mechanism for our JWTs. In case of cookies, we can set such security flags as secure, HTTP only, and same site. And in case of HTTP only, it blocks access to the content of a cookie from JavaScript. But there is another problem. In case of hardened cookies, we need to be very well protected against CSRF, cross-site request forgery, because otherwise, again, when we have CSRF, hacker can bypass our security checks. And another problem of JWT is general problem of JWT is token hijacking. We can freely use any valid tokens, and there is no need to check whether a token comes from a valid place, from a valid user. And to protect against token hijacking, OWASP provides a solution based on a random secure value sent in a token, as well as in a hardened cookie. And if you want to know more, please check out the explanation at the OWASP cheat sheets. Basically, OWASP stands for Open Web Application Security Project. It's a non-for-profit organization that provides various resources for developers to increase awareness of security. And this is only the tip of an iceberg when it comes to JWT security. In addition to algorithms, implementations, protecting against eavesdropping, XSS, etc., we should consider also logouts and timeouts as sort of a basic hygiene for safe application. And unfortunately, in case of JWT, it does not provide any built-in feature to revoke a token or expire a token after inactivity period. So again, it's up to developers to implement those things correctly. And remember, a fool with a tool is only a fool. We developers can't be fools. We need to know how to use our tools wisely. And in software development, we have continuous integration, we have continuous delivery. I always talk about continuous refactoring, but the fundamental paradigm is continuous learning. So as developers, we must keep learning. And that's all for today. Thank you.